So, good morning. This is Bill Crombie. I'm Director of Professional Development with the Algebra Project, and what I'd like to talk to you about for a few minutes is really the last of three seminars, webinars that I gave, looking at different aspects of mathematical practice and formative assessment. So the first seminar was really focused on helping students make sense out of mathematics. During the second webinar, we looked at certain non-cognitive skills which support the doing of mathematics, and in particular, we were looking at attention and persistence. And in this third and last webinar, we looked at the issue of communicating mathematics, specifically through pictures, words, and symbols. And I should emphasize that, these three topics all had the purpose of finding out how we can better know what students know, right? So it comes under the general rubric of formative assessment. This is the abstract for that last seminar, and one of the, I think, issues around communication is that it's kind of like the air we breathe. It's always around us. We hardly pay any attention to it until something goes wrong. And so what we wanted to do during this webinar was to really talk about some aspects of communication in mathematics which don't often come under close inspection. And at the very end, we'll look at least one example from the mathematical challenge that we used during the webinar of how these particular aspects of communication that we're concerned with are related and enhanced and supported, right, in the mathematical challenge. I think we'll look at a first grade challenge. So let me move to a puzzle. During the actual webinar, we actually talked a little bit about communication with participants, about communication in the classroom using pictures, words, and symbols. We were particularly interested in what they would like, not only what happens in the classroom around communication, but what they would like to happen. And that discussion led into this challenge, which let me take a moment to explain. This is actually an example that was developed by Richard Skemp, who was a mathematician and a psychologist in England. And he has a very nice little book that's been republished here in the States. It's called The Psychology of Learning Mathematics. The learning is missing from the title there. And in that little book, he talks about some issues with symbols in general and mathematical symbols in particular. So the puzzle that we put up gives a little dictionary that Skemp develops for some symbols and their meaning. And this is before we actually get to mathematical symbols. So it's meant to be, symbols that you might see in the general culture. And he implicitly puts them together. So the circle that you see here simply means the container. The verb moves, water, write, knowledge, apparatus, controls. That I figure refers to a person. And then this wire has the meaning of electric. And in the 21st century, this was written in the 1970s, but we might also think of that electric as electronic. And he gives some examples of how these symbols may work together. So if you have a container that moves, we typically call that a vehicle. A container that moves on the water, a ship. Knowledge that moves, right? Stem suggests that we interpret that as a message, and this last combination of symbols, when you write a message, knowledge that moves, when you write a message, we typically call that a letter. So, given those examples as hints, the problem that we ask people to consider is what these symbols given below mean, and should point out that this kind of double parentheses, he also introduces, and by that he simply means plural, more than one. So we had a little discussion around during the webinar, what these symbols mean, and let me kind of share the upshot of that with you. If you remember, the I means a person who controls a container that moves on the water, so a person that controls the ship, it's a sailor. And below this, here's a person that controls many persons that control a ship. The interpretation of that we worked through was of a captain. This one, these first three symbols, which you remember from the last slide, indicated message. And so this is an electronic or an electric message, and typically, today at least, we would call that email, right? This is an apparatus or machine that moves many messages. So there are a number of interpretations for this. You could consider it the computer that you send your email out on, but today it could also be a smartphone or a tablet. This last one, here's a container that moves, is the vehicle, and this is a person that controls the vehicle. So we typically think of that as a driver, right? So for an automobile, something. And then the last symbol, we have this symbol for vehicle, a container that moves, and many of them. So we're looking at many vehicles. And here's a symbol. This is an electronic apparatus that controls the movement of vehicles. And after some work, what we get to is at least one example of that is a traffic light. Right? So these symbols are relevant to mathematics because if you notice, one of the things we're doing is each individual symbol represents an idea, right? Unlike the alphabet, which represents a sound. But the symbols in mathematics are like these symbols in that each symbol represents an idea. And when you put the symbols together in some fashion, you're able to represent more complex ideas. Now, what we then looked at was actually an example from mathematics, from arithmetic, really. This symbol is a 3 and then a long line under the 3 and then a 4. And the idea is that in many ways, this symbol acts just like the symbols in the puzzle that we were looking at. Particularly with regards to interpretation. So let me show you an example of that. Very often this symbol is read as 3/4, but it has a number of different meanings. And a few, I think most are just listed here. We could be talking about 3 equal parts out of 4. We could be looking at a kind of ratio comparison of 3 compared to 4. We could look at really something which is 3 units long measured by something which is 4 units long. We could be talking about groupings of 3 out of every 4. We could be talking about a compound operation, multiplication by 3 and then division by 4. And one of the issues around this symbol is that when we do read the symbol as 3 over 4, there's no way for students to tell which of those, 5 different interpretations of this symbol 3 over 4 we are actually thinking about and using. And this arises because of, I guess you could say, what is both the strength and the weakness of symbols in mathematics. It would be very nice and very easy if there was a one-to-one concept between concepts and symbols. It would also be relatively easy if there was a one-to-many relationship between concepts and symbols. That is, if the same concept was represented by different symbols in mathematics. And this often happens. But confusion arises because it's often the case that we have many concepts that are represented by the same symbol. And that example of 3 over 4 is an example of at least 5 concepts that are represented by the same symbol. And this has implications. If we think about the different types of symbols we use, when we use the alphabet to represent words, the alphabet represents sounds. We put those combinations of sounds together to form a word, and the word tells us what we mean. So if I was hooked on phonics, I might take the example of C-A-T and the sounds associated with that, C-A-T, and put them together, cat, cat, that forms the word. And depending upon the context, we're either talking about a feline or a jazz musician. But the symbols of mathematics do not work like the alphabet. As a matter of fact, from the last slide to this one, you see, in some sense, the symbols of mathematics work in exactly the opposite direction. When we look at a mathematical symbol, because they represent concepts and not words, we need, within a given context, to determine the meaning of the symbol. And once we've decided what we want the symbol to mean, we then encode that meaning by choosing the appropriate word. So, in reading mathematics, in a sense, we are performing a process which is in many ways the opposite of when we're reading a simple text, at least with respect to how symbols are related to words and their meaning. What we want to do, or what we did then, was to look at a particular example of how symbols, words, and meanings act together in a mathematical challenge. And the challenge that we really worked through is this one. It was for the first grade, entitled Cookies at the Bakery, and it was really about a challenge about place value. So I want to quickly show you one of the pages, which I think is a good example of how the mathematical challenge uses mathematical symbols, pictures, and words in close coordination to help kids make sense out of the problem they're solving, but also to help them make sense out of the mathematics that's involved. So there's the tray of 36 cookies here. This is actually the page that shows the solution to a portion of the solution to this problem. And what's happening in the problem is students are given a tray with 36 cookies. They have boxes that will fit 10 cookies at a time, and they're trying to figure out how many boxes they need for the cookies on this tray, and if any number of boxes are left over, right? So there's a picture that actually has the 36 cookies there. You see that in the picture, they can actually encircle groups of 10. And at the bottom, they're going to write this in mathematical symbols and in words. And for the first graders, right, it's important that what's happening here with the mathematical symbols is that they're really learning how to write place value symbols. So the 10th place is really corresponding to a box of cookies. So you see the word box under there 3 times, 3 boxes, 3 tens. But you also see that that's supported by the picture that they can draw around, namely 3 boxes, irregular boxes enclosing the 30 cookies, and they can actually see the 6 individual cookies left over. So we were kind of very concerned in this challenge to show the rather tight relationship between these 3 concepts of pictures, the words that go along with the pictures, and the symbols that then express what students see in the pictures and are described by the words. There is, if I can go back to the PowerPoint, I wanted to end with a quote that I shared from a mathematician and philosopher, Alfred North Whitehead, in a beautiful little book. It's called An Introduction to Mathematics. It was written about 100 years ago in 1910 or 1911. And in this book, Whitehead says, by the aid of symbolism, we can make transitions in reasoning almost mechanically by the eye, which otherwise would call into play the higher faculties of the brain. It is a profoundly erroneous truism that we should cultivate the habit of thinking of what we are doing. The precise opposite is the case. And then he says something which at least I found initially surprising, which is why I put it in bold italics here. Civilization advances by extending the number of operations which we can perform without thinking about them. We're presently calling, that goes under a number of different names, right, such as fluency, automaticity. And I think if you think about it, that is very much true. We want to extend the number of operations which we can perform, which our students can perform without thinking about them. What's important about communicating in mathematics is we can only do that if the mathematical operations that students are engaging in is first well understood, if students have first made sense of them, if they are able to connect the meanings between the pictures, the words, and the symbols. If we can help them establish a solid foundation around those 3 aspects of the mathematics we're communicating, then they will indeed be able to perform these operations, these elementary operations, without thinking about them. I want to thank everyone who participated in the seminar, and keep on pushing. Thank you.